Thank you, Vivek, for presenting the video. It was very informative. I'm sure it was informative for everyone who has joined today. Now we would finally start with our webinar. And once again, a very, very warm welcome to everyone. Thank you for joining us for today's webinar. I'll be your anchor and moderator for today. My name is Parita Limbar, and I am working as a business analyst at Vedanta Limited Aluminium Business. In the webinar today, we will be presenting on the theme of the metallurgy of extrusion in association with Vedanta Limited Aluminium Business. The webinar will be mainly covered by our eminent speaker and expert from the extrusion industry, Mr. Jonathan Pangborn, who will focus on process and quality optimization of extruded products. Global extrusion market is growing at a CAGR of 2.8%, and extruded products having a wide range of interesting applications in industries like electrical, construction, automotive, aerospace, etc. We firmly believe that this webinar will provide you with more useful insights about technical side of the extrusion industry. Before we get started, if you have any questions or queries during the presentation, please type them into the Q&A box into the Zoom control panel. We will be bringing them up after the presentation when we have the Q&A session. Over to our first speaker.
Thank you.
Please allow me to invite Mr. Alok Ranjan, our Chief Marketing Officer at Vedanta Limited Aluminium Business, to deliver the welcome note and set the context.
Sure. Thank you, Parita. So once again, a very warm welcome to all the participants. I think last time when we met on a similar exercise, it was almost a year ago. And a lot has happened since then. I mean, India is truly and really becoming a manufacturing powerhouse. And while there's a lot of headwinds in other parts of the world, in India, we see very healthy growth rate. And we hope that this process is irreversible and we'll continue to see, irreversible growth prospects in India. So this is the series of, customer technical service, or CTS team led by Ram. Periodically, we anchor this for our esteemed customers. So this is a class on extrusion metallurgy. This is a request which we keep on receiving from our multiple customers that we should hold similar exercises. And this is the third edition of our extrusion masterclass, which we are holding. And I assure you, and we have had very positive feedback from all the participants in the past, but we very eagerly request that please let us know if we are on the right direction, if you want us to do something more, if there are some specific areas and queries which we should answer. So we'll be more than happy to address all those questions. So that's the background, and I really hope that you have a very fruitful engagement for next 1 hour. Please feel free to ask questions, and we'll surely get back to you. So what I'll do in next maybe 5 minutes, I'll take you through what has happened at Vedanta. So we have a couple of slides which I can take you through. So next page, please. So now we are truly emerging towards becoming a 3.1 million ton aluminum company with fully backward integrated operations with mines and also 100% value added product. So that's the vision, and finally it's taking shape because investment is on the ground and work is on progress. So sometime next year, by end of next calendar year, we expect that all our planned expansion, planned investment will come through and will be maybe second or third largest aluminum company in the world. Next page. Again, we are a company which has full bouquet of services, so right from commodity ingot to various value-added products in form of RP, billet, coils, so everything. So under one roof, we are in a position to cater to the requirement of entire aluminum industry. And aluminum, as we know, is highly versatile, highly diversified in its application. And today we are in a position to cater to most of the applications. Next page, please. So we take a lot of pride in few things, that we are a company, and generally metals and mining need not be something which is incongruous to sustainability or entire natural ecology. So we are very mindful of that, and we take a lot of steps. We walk that extra mile to ensure that we truly are considered a responsible company. And there are multiple steps which we have taken. So last year, as we speak, we became ASI certified. All our products from Vedanta SEZ is actually we have certification under environmental EPT. So EPT is certified. Then also, last year we started selling green aluminum. So and some of the green aluminum which we produce has the lowest carbon footprint. And we have also started supplying that in India. So we encourage all our customers to engage with us, and we are in a position to supply green aluminum. So whosoever our stakeholders have businesses abroad, because this is gaining more sensitivity outside India, but very soon I think we'll see this awareness slowly coming through in India, and this will become a requirement. So we are well positioned to serve green aluminum with lowest carbon footprint in the world to all our esteemed customers. Moving on. So I just said that some of the things which gives a certification of our commitment to sustainability is as follows. Consistently we rank among the most sustainable aluminum companies in the world. So we have been ranked second consistently. First Indian aluminum smelter to have ASI certification for sustainable operations. So EPD for all entire product range. And another thing, some of you would have heard that it has become mandatory to have all the products BIS certified, because there is a quality control order which is promulgated. Although I think there is some time which has been given, but we were ahead of the curve and we were one of the first companies. So entire product range today is BIS certified. Next page. So again, full range of billets from 6-inch to 12-inch, best in class technology with various alloy offering. And again, we are very eager to understand what is the requirement. And we have a very active center of excellence and R&D team working very closely with us. And today we are in a position to offer any kind of alloy. So if there is any specific alloy which is required, we are more than happy to work with you and develop that product for you. Next page. And this is we have very aggressive, ambitious plans to increase our production capability for billet. From current 450, we want to go in excess of 1 million ton by next year. So this will make us one of the largest billet producers in the world. Next page. As I said, reiterating that some of the strengths, some of the key things which we would still like to emphasize is that we are consistently innovating, because innovation is at the center of our product development strategy. And we have been, over the years, developed lots of new products like high-speed billet, high-strength alloy, machinable alloy, various series of alloy, and finally crash-resistant alloy, which finds its application in diverse industries. So right from automotive, defense and aerosystem, building and construction. So all walks of extrusion industry, all walks of building and construction industry. There are very specific requirements, and we have sustainably able to produce all those billets for our customers. Next page. So is that all? Yeah. So that was what I had to convey. But I'm sure the next part of the session is very technical, which is the main objective, the main agenda for today's session. So Johnny, some of you would know, is an expert, and we have been taking his services for quite some time now. And again, re-emphasizes, if there's any specific agenda, if there are any specific issues which you would like us to hold some specific technical sessions, we are more than happy to do that. So that's all from my part. Over to you, Johnny.
Thank you so much, Alok sir, for the brief presentation. Now we will move forward to the main discussion. And in order to do so, I would like to invite our industry expert and speaker of the session, Mr. Jonathan Pangborn. He has more than 22 years of experience in metals and aluminum extrusion industry. In his illustrious career, he has worked with many renowned extrusion plants in North America, like Hydro Aluminium and Gordon Extrusions. He has done his master's in material science and engineering, focusing on metallurgical aspects of hydroforming of aluminum alloys. He has authored several such technical papers on developing new applications, optimization of extrusion processes, parameters, and more. So over to you, Johnny, to take us through your presentation.
Johnny, you are on mute. Please unmute yourself.
Can the host unmute him?
Okay, good. Can you hear me now?
Yeah, we can hear you now.
All right. And yeah, so I'm very excited to be a part of this continuation on a series in metallurgy via extrusion. Thank you for the kind introduction, and we will get started here. We have previously talked about temperature control in the extrusion process, and we will touch on that briefly, but really the bulk of what we want to talk about today, based on customer inquiry, is on extrusion defects. So that will be the bulk of the presentation, with a specific segue into metal flow and planned scrap, really as a part of the extrusion defect discussion. So here is an overview of the extrusion process. Many of you have probably seen this before. But we see here in the extrusion process, the main steps of preheating, extrusion, cooling, and the aging process, and having respect for the critical range where magnesium and silicon grow undesirable particles. Because really, and I should point out, this is the scope of direct extrusion of 6,000 alloys. Other alloys are going to behave differently. For example, some of you are using 3,000 alloys, but a lot of these quality aspects are still going to apply. I do want to change my pointer. There we go. But with 6,000 alloys, in addition to a forming process, we have a metallurgical heat treatment process. So I want to remind us of that we need to be cognizant of that all the way through. And even though we're not speaking of strength levels and so forth in this presentation, there are effects on the surface as well. So here's the quality issues we wanted to highlight. I've divided them into ones that are more strongly affected by temperature and those where there's much less effect on temperature. I won't read those off. Many of them are undoubtedly familiar to many of you. Let's start by looking at tearing. And this is important to touch on, not because it's necessarily the most common issue, but I believe it's not always well understood. To me, tearing is specifically a temperature-related phenomenon, whereby we actually are getting the initiation of melting, or at least very, very close to it. And it's characterized by this type of appearance, where we have these lines transverse to the extrusion direction, where the metal is actually starting to come apart. This is quite different than many of the other phenomena we'll look at. But basically, this is something we see, especially on sharp corners of dies and so forth, or at screw bosses. And in order to avoid this, we really need to look at the temperature control locally at that detail, and perhaps make adjustments to the process to avoid this. I would encourage you also to look at dies. If you have a die that is sensitive to this, work with your die shop, work with your die vendors. Really what you're doing is trying to even out the flow across the profile to try to avoid this. Moving on into pickup. In some cases, very severe pickup is termed tearing, but I want to be careful to differentiate those because the processes by which those defects are formed are very different. So in this example, this isn't highly severe pickup, but this is starting to be a problem here in this example. In this case, this is a simple flat bar, and we have one side, and you can this is just some handling marks from people handling it, but basically this surface here is acceptable, and on the other side it's not acceptable due to this pickup. It's a very complex defect, but fundamentally it's forming in the die as you're coming off the die bearing, and we'll have a diagram in a moment here. And it's sort of spalling off, and in fact sometimes you can see like this type of pickup here that actually it's very lightly sticking, and more than likely you could actually brush that off with like a gloved hand or like a little piece of cloth or something, and that would actually fall right off. It's very weakly adhered more than likely. Some of the factors that we look at when we have these problems are with the die, primarily, looking at the shape of the bearing, making sure that it's the correct shape, that it hasn't been rounded, that your die bearing angles are controlled, and then also your treatment of it, specifically for most products, it's going to be a nitriding. There's other coating technologies, but usually it's nitriding your tool steel and making sure you have a very hard, resilient layer. Extrusion process parameters also will have an effect, but not necessarily in a controlled or predictable way. I would say usually higher temperatures and sometimes faster is better, but that's not a bulletproof solution, because as you're changing those parameters, you're changing the shape of the die in subtle manners, the way it is deflecting, how the metal is coming off the die bearing. There can be billet quality issues, so that's at least something to be cognizant of. These days, the process control has gotten quite good for billet. Generally speaking, it's not a problem, but if they're, particularly with homogenization, are problems, it can result in contribution to pickup. So really, and I'll say this multiple times through this talk, if you want consistent results, you need to have a consistent process, and pickup is certainly that. You are all of you who are extruders are extruding parts that maybe nobody else runs, that are going to be very specific to your press, your dies. But once you find a process, stick with it. Also, avoid running billets too cold or speeds too slow. Sometimes that seems counterintuitive. Most press operators and even press managers, when dealing with these type of problems, the first indication is to slow down. And that's one of the reasons I wanted to make a distinction between pickup and tearing. Absolutely, with tearing, if you're overheating and having tearing, like we talked about on the previous slide, yes, that is a situation where you want to slow down. And then again, I mentioned die bearings, but particularly avoiding rounding the die bearings, and that could very easily happen in the polishing step. If you are, as most extruders, you're polishing manually, it's almost impossible to keep it perfectly flat. And if you have rounded bearings, you'll undoubtedly at some point run into surface issues. Moving on here to die lines. This is actually fairly closely related to pickup, even though the appearance is quite different. In fact, in this example here, this first image, we see die lines, but we also see fine pickup that's closely associated, and maybe it's difficult to see on some screens, but you can even see that they are aligned where the pickup is and the die line are in the same position on the part. That is not uncommon, but it comes and goes. In this example here, there's not so much pickup as well, just die lines on this part here. This is again similar. but it's more related to the die bearing itself. As we're extruding, the aluminum is not actually sliding over the die bearing. There's actually an adhesive layer that forms, and it's not necessarily a reflection of the die surface, these die lines, but it's a reflection of that adhesive layer that is formed on the surface. So again, with rounded bearings, there can be a big effect that adhesive layer may be unstable and inconsistent across, and we get die lines. Extrusion process parameters affect that dynamic, again, in not necessarily a predictable manner for a given product. And then I would say it's more rare maybe than even pickup, but billet quality certainly could have an effect. For example, if you have very, very large iron-containing primary phases that are arranged in that adhesive layer, and they're sort of reaching up and scratching, if you will, the finished surface. So the actions here are quite the same. Generally, having a consistent consistent process in extrusion, following your die nitriding or other hardening practices, making sure the die polish is not excessive. Ram, you wanted to bring up someone's question here?
Yeah, sure, Johnny. So, hi, good afternoon, everyone. I am Ram. I am heading the customer technical service of Vedanta. So I was getting continuous questions, so that's why I paused Johnny for a minute. So, Johnny, the basic question that comes for die lines is there two types basically when we see. One, during a continuous process, intermittently, the die lines come. And second, you load a new die and you find die line immediately. So how do you tackle these two situations simultaneously? Can you?
Yeah, that's a excellent question, because these are very common, and at times that is the case where you load a die and you start running, you immediately have die lines. One thing to be at least cognizant of is whether you are storing metal in the dies from the previous run. I actually believe that is a good practice if you control it. However, whatever surface issues you may have had or been starting to have towards the end of the previous run, if that's not communicated properly that a die needs to be cleaned out, you could end up with a continuation. So it's analogous to if you ran whatever 10 billets previously and now you're starting up again from a surface development perspective, you're kind of like starting at billet 11. And this type of issue does tend to develop over time. Honestly, I think at the floor level, you should expect the reaction, unless there's guidance from a manager, for example, would be to pull the die and move on, because it's definitely not just a slow down and get it out, and you don't want to lose productivity anyway from a cost standpoint. But generally speaking, because it is so often die related, it's usually better just to pull off and go. I would say, regardless of whether you're starting out the die or it's developing over time. If you are giving oversight to your teams, I would say there's opportunity to look at your process and decide based on your knowledge of that particular shape. Okay, let's try something a little bit different before we move on. But very, very good question.
Sure, Johnny.
Okay.
Please
Yes, and here is, and I've combined this slide for both of them because they are closely related to each other, even though the appearance is different, as I mentioned. But there's a couple different diagrams, and actually let's look at this one first. This is intended to be the metal motion indicating by the arrows, and this surface here, the die bearing, and then you have the back relief supporting that where the metal is not intended to touch. But as your metal is going over past the die bearing, the conditions continuously change from a high pressure situation to, as the metal departs the die bearing, really there's no pressure, no external pressure on the metal. The aluminum is the profile is self-contained. So as that happens, you have a very dynamic situation where you have a sticking friction, so this adhesive layer that we referred to, and there are a number of publications from different research groups on that are very interesting if you really want to get technical. But there's a sticking region, and then there's a sliding, or it's not really shown here, but I would say even a departure region. If, for example, looking at this other diagram, obviously this rounded bearing is very exaggerated for effect, but if you actually are no longer touching, effectively, you don't have a usable bearing in that position. So the sticking is sort of like this in a rounded bearing. The sliding maybe towards the top and a little past it, where it's either intermittent or it's just not, it hasn't developed that adhesive layer. So the die lines are forming primarily kind of at the top of this, or if you have a flat bearing, properly flat bearing, it's going to be on towards the departure side of that. So if you have inconsistencies in how the metal is departing from the bearing, or you have particles embedded or something, you're likely to get die lines. Pickup is generally forming where it can be oxidized. So on a rounded bearing, it can be forming here, and very often it is forming actually on this back relief here, and you may get very large pickups that build up and then suddenly stick to the part and come off. And I did have, this is at least a small example of that, but maybe you've seen very, very large occasional pickup that you can actually see this back relief embedded in it as it forms. So this is at least the fundamental understanding of pickup and die lines. Yeah, I did mention the bearing rounding is probably the single biggest factor that you need to look out for, that is at times is not a controlled parameter at extrusion plants. You're controlling temperatures and speeds, for example, but you may have some inconsistencies in the dies that are coming out. Orange peel is, yeah.
Just like to hold on here. One of the questions that I've just received is like, once you received a die line or pickup, what would be your immediate next steps?
The default would be, well, of course, if evaluating whether that may be acceptable for the customer, of course, if they can tolerate a little bit. But if it's deemed unacceptable, you would normally expect your crews to pull off the die and go on to another order, unless, of course, you have a backup die for that profile. Yeah, but you don't want to waste time going back and forth and making scrap unless you have the resources in place, the right supervisor or manager or an engineer or something, where you're able to make adjustments to the process and have a good chance of really learning something from that. Oh, and I should mention, I think it was in some of the text in the slides, but you can actually, we haven't talked about actual lines in the die bearing, but of course, if either due to polishing with heavy grit paper, or from wear to the die, from getting what I've heard called washout, where you actually have physical lines in the die bearing, that of course will affect the die lines, obviously, but most of what we're talking about is more subtle than that. Okay, moving on to orange peel. This is another common issue, particularly on heavier shapes, and is basically related to the grain size of the part. And then when you're deforming, the individual grains in the material are because of crystallographic orientation, they have ways that they want to be arranged, and so they kind of rearrange themselves a little bit. And it's enough on large grain material that you can actually see a visible representation of that. So here's a case where it's very severe on a part that undoubtedly has large grain structure and then also has a pretty good bend on it. but it can be even due to stretching on the press line. Here's an example here of kind of a normal, you can see a little bit of grain deformation, but it's not probably for most parts not excessive. And then right next to it, and I don't know why this happened, but undoubtedly there was a difference in grain structure. Maybe they had a delay in the process or something. The adjacent part in the rack is having grain structure, and it clearly has larger grains. Usually this is basically always going to be more prominent on a thick part. If you're running BNC thin wall window frames, you're unlikely to have as much of a problem. It's usually if you have a larger, thicker part. Generally, your grain structure is going to be faster, better running faster and hotter. But again, it's a dynamic situation. There's many kinetic factors that are contributing to it. So it's not a hard and fast rule. In particularly, anyone who's running 6082 often needs to run a colder billet temperature to maintain good grain structure. For example, a good minimal recrystallized layer at the surface. But different profiles and different alloys will behave differently. And it's really, again, I said it before, but a consistent process, finding out what works and what sticks with it, and really understanding, not at a first order, but really at the second and third order, making sure that there's consistency. And for example, in this last point, quenching is important for some alloys, and really it's the time between extrusion and quenching that's important, which is probably can be the most apparent problems if you have a delay at the press. So for example, whatever, the puller lets go of the part, you have to stop the press. There's something happens similar to that. And then you have recently extruded hot metal that's sitting between your platen and your quench. And especially that it tends to be heavier shapes that have the problem to begin with. Often it's water quench that is not happening, and it's being delayed for some time.
So, Johnny, one question has popped up just now.
Yeah,
asking,
for sure.
If we reduce the billet temperature before putting it into the container before extrusion, will that help in the reducing the orange peel off?
I would say generally no, but there are many factors that go into really the more energy that you can put into and it's not electrical energy, but energy of work that you put into the material, the better, the finer the grain structure is going to be. And you can put that energy in really two ways, is with temperature and with work for deformation, which is your strain, but it also is related to the resistance to deformation of the material. So as you go higher in billet temperature, you're starting with more energy in the material to begin with, but the counterbalancing factor is that it's also easier to deform, so you're putting less work energy, right? We know at a press, if we increase our billet temperature, it's easier to push. It takes less force from our press to do so. So there's not one right answer, but in my experience, the hotter temperatures for really any of the 6,000 alloys except 6082 is going to be a benefit, although there will be exceptions on some product. I will say 3003 is also going to behave quite differently. So if you're running like a 3003 or 3102 or something with a high manganese content, in those cases, you may be better served with a lower billet temperature.
Right, and I think in a single question you have answered two more questions. One was if this is applicable to 3000 series alloys as well, which you have just said that yes, higher manganese content can play this role, and whether there will be some role to play on the grain sizes in the orange peel off issue. So I think you have also spoke about that, how that can impact and how we can optimize that.
Very good.
So I think you may please go ahead.
Okay, perfect. All right, moving another common issue, blisters, a much different issue. This is not a metallurgical issue, and while temperature can affect the way the metal flows and where you could consider the air or oil that's trapped in the blisters a form of contamination. It's not, net temperature control is not causing this. It's about avoiding contamination of the process. These, of course, are air, possibly oil, that is in the process, and when the pressure of the die is released on exit, you very often can hear these blisters pop out, and you know, we'd audibly hear that there's blisters forming, and then you look and you see them. But it's basically controlling what's going into the container. There's anything going into the container, of course, it has to come out at some point. And for air, for example, every time you're loading a billet, you're also putting air in there because the billet is not a tight fit. It's a very loose fit to the container, which is why, you know, we run a burp cycle, upset the billet, and then release the pressurized air, and why we pay attention to the sheared surface and so forth. It certainly can sometimes be related to transverse weld, possibly coring, but that's less likely. And I think it's mentioned later, but make sure that it's mentioned here. Split billets can be an issue for blisters, in particularly if you have, for example, a log shear and you have a high level of deformation on the front and back surfaces. This will definitely be more of an issue for sheared metal. And I would say if you have a shear, that's probably what you're going to stick with, but making sure it's well maintained, that the shear blocks are properly cutting, and you're doing the least deformation you can get with a shear. With regards to lubrication, that's an action to avoid excess lubrication. Sometimes I think our operators feel like if a little lubrication is good, more is better, and that is not the case. Just the proper amount. Again, it's not necessarily a recipe parameter, but it is a factor that we need to control in our process, and having a clear understanding for what lubrication we're going to use for what part of the process, and making sure that it's done in a controlled manner. And in general, making sure equipment is clean, it's aligned, it's working smoothly, because there'll be less of a temptation to have excess oil or lubrication in the process, as well as we'll have a consistent burp, and we're more consistent shear, and we're more likely to have a repeatable process. And I do mention here the billet upset and burp cycle, making sure that those are set up properly. So we're removing all the air at the beginning of the process. Here's some examples of shearing. This is, I would say, kind of a classic poor shear that is not well aligned, probably due to just the equipment is old in this case. It's hard to align it without it hitting the top of the die. It's really scarring the surface, and then you can actually see a little bit where these arrows indicate that metal is pulling out of a pocket going into a hollow, and there's going to be some blisters associated with that. And this is a quite special case where the shear actually looks generally pretty good, except there's a pull out right in the middle, and this is very deep. Any of the air in there, the next billet's going to seal that in. It's very unlikely to be able to burp any of it out, certainly not all of it, and we're going to see blisters probably towards the front end of the extrusion run out. That's actually another thing to consider. If your crews are reporting to you that they're getting blisters, ask questions like, where? Is it at the front end? Is it the back? Is it every billet? Because that is a very important to problem solving on where blisters are coming from. Because they can also happen anytime we aren't getting the air out. Moving on here to coring. Your container is set at a temperature, hopefully it's well below your billet temperature. to arrest the flow of the surface layer, the segregation layer, or as it kind of is roughly termed, billet skin that is on the surface. At the container surface, you really have almost zero metal flow, and then towards the middle, of course, the billet is moving much more easily. I think of it as analogous to a river. Of course, if we have a river near where we live, we know, we look at it, if we're out in it on a boat, whatever, it's moving much more quickly in the middle than on the sides. That's a good analogy for what's happening here. And in particular, if we have good temperature control in our container, this black here is representing that billet skin. Rather than proceeding to flow into our dies, it's being collected in the back of the billet, which ultimately most of it is removed when we shear that butt off at the end. However, in order to actually get all of it, even with very good billet quality, very, very state-of-the-art, we would have to take like 4 inches, 100 centimeters, and then we have other problems. For example, the blisters we just talked about. So in practice, we have the shear coming down, taking the butt off, and most of this billet skin, but we're likely to have some of it in the die or in the profile on the next step. And then when we add a new billet, of course, anything that's in the die is going to push out. Remember, anything that goes into the process has to come out. By cutting that butt off, in addition to the pressure buildup and so forth that we can't have for pushing to a paper thin butt, we're purposely removing the majority of this. But in this example here, a weld pocket and a stop mark on the extrusion, what will happen is anything that goes actually into the extrusion will be in the billet that was pushed. Anything that is remaining in the die, you won't see. You'll see it on the other side of the stop mark on what we would call the second billet, the billet following, but is actually still cleaning out in front of the transverse weld some of that. This is important for some products, but not all. We need to be careful with structural and especially heavy structural products where these impurities are not able to break up, and due to a high extrusion ratio, but with a low extrusion ratio dies, these can be very important. Of course, automotive or structural, any of you that do precision tubing, of course, would have to be very careful with this, with your thin walls. And there needs to be a mechanism to cut this out. If you cut on the stop mark, it's gonna look like this, where you have a transverse weld, which is difficult to see in this graphic. I don't know if you can see that on, yeah. And then you have inflow, and then it's proceeding into the front of the previous billet, which is actually the back of the previous billet, which is showing the back end of the runouts. So understanding how much scrap you have to take and following that is extremely important when it comes to these type of products. I mentioned some of these type of products before. There can be others as well. These requirements can be determined experimentally quite easily, actually. For example, if you go from your stop mark and cut periodically, whatever makes sense for you, every 10 centimeters or every 20 centimeters, and etch it even in your caustic, if it's fairly fresh in your die shop, you will be able to see this and make some judgments on what's acceptable experimentally, and then making sure that it's followed and that your press crews understand the reasons for that, so that you avoid risks downstream.
We got again a couple of questions on coring.
Oh yeah, please.
When you are talking about coring, I think piping is a similar kind of defect, and in other languages it's the same thing. So there
Yes.
was
Yeah, that's equivalent terminology is also called piping, and I believe it's because if you have like a very heavy shape like a rod or something like that, that's what it will look like. It'll look like a circle in the middle, very, very dark circle after etching, like a pipe.
Right. So there are two questions that has pop up. One is with respect to the blister, the burp cycle specifically, that how can we decide upon a proper burp cycle? How do we know, okay, yes, this burp cycle is actually working for us?
Yes, I would say most of the time, if you you have to start with the blistering side of it, is making sure that you're getting a good shear on there. And generally, if you get a thicker butt, it's going to be harder to shear. So very often, even places that are doing critical products, they're still using, and this is, you know, not metric units, but they're using, like, for example, a 1-inch butt, 25 millimeter butt as a standard. And then they're adjusting for that in their scrap zones. So like in the graphic we're talking about here, they may be taking more scrap in the back end here to account for that, but they're making sure, first of all, that they're getting a good shear. I feel like most presses I've seen, 2, maybe 2.5 inches, 65 millimeters is probably about as far as you can go on basically any shape, or else it's really just going to pull out and leave voids in the air pockets in the die, which are then going to result in blisters. There are some things you can do on die design to try to make it difficult for the metal to pull out of the ports by putting some tapers in there. But even so, that doesn't get you a lot. You're not going to be able to shear suddenly a 4-inch butt, 100 millimeter butt, and get good results. So I would say approach it practically for that product and that die. If you have a nice wide feeder and you're running a solid die, you probably have more flexibility than if you're running a hollow with big ports that are pulling out. And then controlling that, making sure it's consistent. Again, process standards, making sure it's controlled, and then you're taking the appropriate back scrap here to make sure that any problems are removed. Does that feel like that answers the question, Ram?
Yes, that answers the question. But again, a similar question pops up. Mr. Guru Prasad had asked, for the coring defect, what will be your recommended butt discard at the extruded so that coring doesn't pop up?
I think if you actually wanted to avoid coring in the extrusion completely, you would have to use like you know, at least 11, but probably 14-15% of the total butt length, or the total billet length in the butt. So if you're running a 30-inch, help me out here, but if you're running a 30-inch billet, you'd have to have 4.5-inch butt, which isn't really practical. So it's to me, it's not necessarily about avoiding coring, it's controlling it. You're controlling where it is and knowing where it's going to be so you can deal with it, rather than attempting to keep it completely out of the die. Yeah.
Sure, I think that answers the question. Okay. Please proceed.
Here's some examples around the end scrap, and this is a really interesting one because it actually shows 3 different things that are related that we've talked about. One is the transverse weld, which really is this inside line that you can see very clean metal. The first line here is the interface between the 2 billets. Right outside of that, kind of analogous to what we're talking about here, is the coring, this sort of more fuzzy, dark stuff. And in this case, there's actually a blister associated with this transverse weld at the same time. I don't think this is the same part, but it shows more macro, some of the similar effects. And in this case, it actually shows after anodizing these very, very ugly streaks that are occurring due to that inflow. So I'm glad I have this in here, because it also, on the flip side, we've been talking more about mechanically critical parts, but of course, if you have aesthetically critical parts, you don't want to have this inflow. The transverse weld really isn't a big deal, because you're not running a heavy structural product, but any inflow that gets onto the surface of your part through this flow mechanism is going to cause problems for sure. But again, controlling that by having enough scrap. So I know for specific examples where I can think of where I think we had increased on one particular black anodized product line. It was really for everything we did for the one customer. We went from 1 inch to 1.5 inch butt to push a little bit less into the die, and then we increased the scrap requirement at the back. I'm not positive on the numbers, but something like from 3 to 5 feet, and we avoided having, which in the black anodized showed up as these white lines. We avoided that completely and fixed the issue that was plaguing us at the time. Yeah. So in summary, and I think we'll have a few minutes for questions after this as well. We went over this briefly over the extrusion process steps, primarily focused on 6,000 alloys, though most of what we talked about is applicable to other alloy systems as well. Spent most of the time here, of course, talking about extrusion defects to try to understand the causes, and again, emphasizing minimization of process variation, and then a little bit on metal flow in the billet related to defects and specifically why we control scrap zones for certain products due to the sensitivity to these defects. Yeah, okay, very good.
Thank you so much, Jonathan, for such a detailed presentation. Like to request everyone who has joined to put their question in the Q&A box. We can, if Ram sir permits, we can answer a few more questions, sir.
Sure. Thank you, Parita. So, Johnny, I think there are a few questions coming up with respect to coring defect. One of the major being, how do you identify a coring defect? What are the mechanism or the methods to identifying a coring defect that, yes, there is a coring in the extrusion? Yes.
The experimental method that I referred to is maybe crude is a heavy word, but it's very basic, and it's something that most extruders can do if they have a die shop, which most of course do, for cleaning their dies out on site. Basically, if there's ever a question, you can cut the cross section and you can dip it in the caustic solution in the die shop. It's going to depend on how clean it is and how fresh and how strong and so forth. But something like 2 minutes or 5 minutes to pull it out and rinse it. You need to rinse it quickly, or else it'll have a lot of buildup on it. It'll make it hard to interpret. But if you have coring, you will be able to see that. Undoubtedly, these examples that I showed the black contamination, that is undoubtedly what they're using, some kind of etch process. It may not be that exact one, but that's something that most extruders can do. And in fact, many extruders that run a lot of this type of product, they have that as part of their standard quality checks. So for example, they're taking a 4-inch 100 millimeter sample at the back end of all their billets that they run for some product, some heavy product, and they're scribing them, because any marker, of course, will be eaten away, but they physically scribe in a reference number, they put them in, and then they're evaluating and making sure that all their product is good. But also, as I kind of very briefly mentioned, I've done it many times myself, where you cut the front and back off apart, the scrap zones, and you can maybe not start from the stop mark because you're never going to do that, but a reasonably short scrap zone, 3 feet in a meter through 2 or 3 meters, whatever you expect to have a problem, verifying that that you have that coring under control. But I want to emphasize that's going to change with billet length. You wouldn't want to set up a scrap zone, for example, using a 2-inch butt and then have issues and go to a 1-inch butt to try to solve a problem, but then not account for that. Because that extra 1 inch of metal is exactly going to translate to however long that it takes to extrude 1 inch, 3 feet, whatever it turns out to be an extra meter. That's approximately how much, or very close to exactly how much extra scrap you're going to have to take. So you're really taking the same volume or weight of scrap, but you have to know if you're changing the butt length, you're changing the ratio of how much is coming, you're shearing off the back of the die versus cutting at the saw. There's in anodizing, you'll very often be able to see, for example, at the cut surface, if you're not taking all that out, you'll be able to see that as well, either on the exposed surface or actually on the cut face, if that's the cut face that was pre-anodizing.
On the similar note, just a small question, you can answer it quickly. Whether UT inspection can give us some light, whether there is coring going or not, the ultrasonic inspection?
Yes, I have never tried it, but I would say for severe coring, it's more than likely to catch something. I think the problem is with coring is it's not necessarily a very defined interface, like a transverse weld at the front end that's contaminated with air or something. That would probably reflect back in ultrasonic. I think it would be fairly hard to interpret with coring, but I've never actually tried it.
Right. So Johnny, I will take some other questions other than the defects. So there was a question that if in a billet there is a normal grain size and there is an abnormal grain size because of whatever process is it, how it is going to impact the extrusion process?
As far are we talking like the billet grain structure coming in, how that's going to affect the process?
Yes.
Is that the question? A smaller grain structure is going to have a somewhat higher deformation resistance, so it's going to be somewhat harder to push. But honestly, I think for most of our processes, it's not going to be notable unless, for example, we had like very severe problems with the grain refining in casting, which other Vedanta casting experts could comment on better than I, but like getting feathery grains or excessive grain growth or something like that. But generally speaking, honestly, I would expect it to be very, very consistent with your billet suppliers, Vedanta.
So, Johnny, on the same line, I think there is a few questions about 6061 billets that how can we achieve the maximum UTS in the hard alloys like 6061 or 6082, but without using the water quenching? Is there a way we can achieve that?
Possibly. It's really not about the method you're cooling, it's the cooling rate that you're achieving. And of course, if we're using water, we're expecting a much higher cooling rate than anything we can do with air. I would say for 6061, anything that's heavy walled, almost certainly have to water cool. But if it's a fairly thin wall, then yeah, absolutely it's possible to air cool depending on the setup. It is of course very dependent on the profile as well as the equipment that you have. 6082 is more quench sensitive, of course, than 6061. That is very difficult to air cool. In fact, I can't think of a time where I've seen that successfully done. I think conceptually, if you had very thin walls and you're achieving a high cooling rate with intensive air, it's possible, but that would be, I think, a very specialized situation. So for 6061, I would say as much as possible, work with what alloy you want from Vedanta for some support on which alloy variant that's offered is most appropriate. But generally, if the problem is quench sensitivity, you would want to have the one with the least amount of alloying elements possible. Yeah, I think that there's some things you can do maybe on a 6061 as far as alloy content for example, manganese levels, to try to adjust something that works for your process. I would say with 6061 strength levels, it's a little bit lower than 6082. So at least if you can work it out with your customer, I would encourage asking if you could, for example, supply 6005A, which is going to not require as high of a quench rate and is generally, you're much more successful air cooling than 6061. But of course, you have to get permission from your customer. However, I've been involved in those discussions and generally I've seen a lot of success in that. Once you show that, hey, we can give the same strength level, but here's why we want to use this alloy. We can be more consistent. We can offer you better product. It's going to look better, and we're going to be more on time and support your needs better. Yeah.
Sonny, I think we are well beyond the time permitted, but
Yep.
I can't help but ask the last question. It was
Sure.
like, if we have a press set which is newly set up, and then with all parameters, if we vary only the chemistry, the silicon magnesium percentage, in the 6063 alloys, so how does the property changes? Is there something that we can predict or we can work on in more advanced way? If you can guide us on that.
And just to clarify the question, are we talking the difference between a current press and a new press, or is it more just any press?
Any press where we are varying the chemistry and we are expecting, how can we expect a different result with respect to the chemistry variation?
Yeah, I think generally speaking, the more alloying elements you have, of course, you're going to have a higher strength, but at the same time, you're not going to extrude as high a productivity. So there's a balance. So the ideal is to have an acceptable strength level that's meeting the requirements of the customer consistently, without going so far that you're having to slow down to do so. I think there's some companies that have some modeling tools that can contribute to that, but on thinking about that, I think it depends very much on your particular alloy and your supplier and your process, where you would need to do some work to supply that to them, and you would get the answer as a part of that. I think Vedanta has, for example, the high-speed alloys and other alloys available that I would start with, and then evaluate and make sure that you're consistently meeting the requirements. And if it looks like you have more than you need, then request some discussion around making some specific adjustments to your particularly on 6063. It's mostly the magnesium silicon levels.
Very true. Thank you very much, Johnny.
Thank you, Jonathan, for answering all the questions so diligently. We have many more questions left, but I think it's our time to close the discussion. Ram sir, I would like to request you to give vote of thanks for today.
Yes.
Thank you, Parita. I think.
Sorry, if I could interject, I just wanted to thank everybody who has been, especially if you've gone past time here and you're still with us. It's a pleasure being able to share my experience with each of you. Even if I am not seeing you personally, I appreciate it.
No, the pleasure is all ours, Johnny. Thank you very much. We know it's very early in the morning, and you spent so much time in preparing this deck and sharing these thoughtful insights with all of us. Thank you very much. And we assure all the participants that the questions that are left in Q&A box, we couldn't answer everything. So we'll get back to you with all the answers on your mail. And thank you very much for your presence. And Johnny, especially how seamlessly you have done this in a virtual environment and connected with all the dots, how extrusion press needs to work on a more efficient way. So your domain knowledge really speaks for itself, and thank you very much with respect to that. Also, I would like to thank the participants who are part of this. I have been really got so many questions followed by one by one, and your active participation really encourages us to conduct this kind of event more frequently. So we'll definitely seek your insights, your feedback to how to make this event more useful for you. We can have more questions, more answers, and take that behind. And also, last but not the least, I would like to thank the people who has worked behind the scenes, all the technical support teams. Thank you very much to all of them. And we really appreciate your time and patience with us. Wish you a happy evening. Thank you very much.